In this video, we will be talking about standard deviation and how we can calculate it when we have data that has come from multiple replicates. When we talk about standard deviation, we want to use this standard deviation calculation to really represent the variation in the data. And so we have an example here of an experiment that was done to look at the birth weights for babies that were born to mothers that indicated that they were smokers or were not smokers. So in red would be the mothers that said that they were not smokers, and you have all of the babies' birth weights graphed here. And so they would all fall within this bell curve shape, and it holds a pattern of what we call a normal distribution. The mean for the data is indicated by the red dashed line here. And then likewise, the mothers that indicated that they were smokers, their babies' birth weights are graphed here under the blue line, and their mean is with the blue dashed line. So if I only looked at the mean for these baby birth weights, and I was strictly looking at this one point between the mothers that were not smokers here in red and the mothers that were smokers here. If I only indicated that one piece of data, then I would say yes, well, definitely the mothers that were not smokers, their babies had a higher birth weight. But I would only be looking at that one point. What that one point is not showing me is all of this other data that's taking in, that's been observed. And it's not showing me the spread of the data. And it's not showing me that there are some babies' birth weights that fall in the same range for mothers that were not smokers and mothers that were smokers. So how can I clearly know that these two birth weights are truly different when there's so much overlap? And how can the data demonstrate this overlap for me so that I can make a decision whether I think that these birth weights truly are different between these two groups? When you talk about normal distributions or bell curves, that's when the population of data takes on this shape, this kind of bell curve shape here. And in a normal distribution, most of the data is going to fall close around the mean. The mean's here in the middle. And then you're going to have some data further away and some data even further away from the mean. And when we talk about standard deviation, which is shown here on the bottom line, you have the mean in the middle, and then you have a standard deviation of 1 above the mean and below the mean. With a normal distribution, the standard deviation is going to represent this population of data that centers around the mean. And with a normal distribution bell curve, it actually is going to hold up to 68.2% of the data. So a lot of the data is here centered around the mean. And this idea of standard deviation is giving us an idea of how far away is that data from the mean. And it will always be encompassing this 68.2% of data. And then if we go 2 standard deviations away from the mean, we're going to collect this kind of light green area on both sides. And if you add that all together, that's going to indicate that that's 95.4% of the data. If you go 3 standard deviations from the mean, then you get nearly all of the data. So when you calculate the standard deviation for your data, it's going to indicate how far away that data is from the mean. And so you can have standard deviations that are lower and higher. And what would happen if you graphed out the data, you would see that the bell curve shape would change. So with a lower standard deviation, you would have a tighter bell curve, and the data would be more close to the actual mean. If you have a standard deviation of 1, the bell curve spreads out a little bit more. And if you have a standard deviation of 2, the bell curve would even spread out even more. So how can we use this in our experiments? Well, we get the honor and privilege of doing standard deviation equations. And the standard deviation equation is shown here. And it looks a little daunting, but we will take it step by step, and you will see that it's really not too bad. Within this equation, just keep in mind that the letter N would be representing the total number of samples taken. The X bar, this X with the bar on top, is representing the sample mean. And the X with the little I is indicating measurement of an individual sample. So just keep those abbreviations in mind. Also, I wanted to just note real quick that today we are going through the equation here, the standard deviation. And just keep in mind that this equation is for samples. There is also another equation that can handle populations, and it's written slightly different. The mean of the population is indicated with a different symbol. You'll notice here that it just says N, it doesn't say N minus 1. And this is because you are taking more measurements from the whole population. Here you're just taking a sampling from a population. And so there's going to be more error when you just represent a sample of the population. You may or may not have a representative sample. And so because of this, there's an N minus 1 here to deal with that extra bit of error. So for our purposes, we will be looking at this equation right here. Okay, so our first step, and what I've done here is I have the same example that was shown in your worksheets, where we had an experiment that was performed in yeast. There was a control group, drug 1 and drug 2. For each one of the groups, there were 3 replicates that were tested. And then the growth of the yeast was monitored using a spectrophotometer to obtain an absorbance reading at OD 600. And the result is shown here. So each replicate has its own absorbance reading. And the first step that we need to do is to find the mean. And the mean is nothing more complicated than just taking each one of these numbers, 4.2 plus 3.4 plus 3.1 equals 10.7. And then dividing by the number of samples. In our case, we had 3 samples, 1, 2, 3. So we would simply take that number 10.7 divided by 3, and we have our mean, which is 3.6. Our next step, so we found our mean, which is X bar. Our next step is to find deviation. And so I'm indicating with this little box in the equation here that what part of this equation is the deviation. Well, the deviation is how far does each individual measurement differ from the mean. So to do this, over here on the right, I've shown that I've taken each one of our samples. Here is the individual measurements, and I have a minus sign, and then I have the mean that we just calculated. And then I find the value. Okay, and I have done that for each one of the replicates. So there we go. We've already found our deviation from the mean. Our next step is to square our deviations. And so now you can see that we're working within our equation. We're taking it step by step. Here was our deviation. We're going to square it and put our results here. So we have our deviation squared. So 0.6 squared is 0.4, and on and on. The next step is to find the variance. What is the variance? The variance is the sum of the squared deviations divided by n minus 1. All right, well, we've already found our squared deviations in our previous slide, right? So we have our deviation squared right here. So we're literally just going to take the sum of it. We're going to add those together. 0.4 plus 0.03 plus 0.22 is 0.65. So we found the sum. So that's the top part of this equation, okay? And that's also been indicated here. And sum is also indicated by this symbol. This Greek symbol is what is representing sum. And when we say sum, we're just talking about adding those things together. And the last step is we need to take our sum divided by n minus 1. In our case, n is 3 because we had 3 replicates. And then we'll say 3 minus 1. Okay, so 0.65 divided by 2 is 0.325. Our variance is 0.325. And the last step is to find our standard deviation. Standard deviation now is only the square root of our variance, okay, which we just found our variance here. And now we're going to take the square root of that to find our standard deviation, which is 0.57. And you can see here in our equation, standard deviation here is equal to the square root of the sum, right, of the deviation squared divided by n minus 1. And so even though the equation looks very daunting over here, we have actually performed all the steps in our calculations over here to the right. And that's it. We have our standard deviation is equal to 0.57. So we've already done our standard deviation for our sample. We've worked our way through the equation here. And that's it. Thank you for watching, and good luck with your assignment.